The topic of this year's TEDx event is monumental perceptions, looking at subjects that alter our entire perspective of the world. In the field of science, new discoveries are constantly made on a daily basis, but few discoveries have drastically changed the scientific community's way of thinking as much as the idea of quantum physics. I am sure many of you have heard the word quantum tossed around at some point, maybe in a movie, or in a high school science class, or in hearing one of today's favorite buzzwords when it comes to advancements in technology, quantum computing, which I'll get back to later as one of the biggest applications of this new lens of looking at the world. If you, like me, grew curious and started maybe doing some research online, or trying to watch videos and find out more about this area, it can be really confusing to try and actually wrap your head around some of these ideas, even if they might seem simple at first glance. For instance, take one of quantum physics' biggest ideas, that all matter behaves like waves at some level. It's really easy to just take this at face value and go, okay, I guess that's true, everything is a wave, and just carry on with your life. But if you start to think about it a little more, questions start rising like, okay, so if I threw a baseball at my friend, then that's also a wave. Why don't I notice this? What makes these waves fundamentally similar and different from, say, the waves on the beach? And how can the same term be used to describe all these things? Is this stage that I'm walking on right now a wave? Am I walking on waves? And this list of questions never really stops. It starts to become almost a matter of philosophy rather than just physics itself, trying to cement these abstract ideas into our physical reality. But I am not here today to take you on a philosophical journey. I am here today to actually try and talk you through some of the physics. So let's start with the name, because I find most people have no idea what this word quantum actually means. Quantum refers to the idea that energy carried by light is quantized, or can only exist in certain allowed amounts. Essentially, imagine taking any arbitrary amount of energy and breaking it apart into smaller and smaller pieces until these pieces can't get any smaller. And that single smallest discrete amount of energy is referred to as a quantum. It can be thought of as a singular Lego. You can build all kinds of structures out of Legos, but unless you start making your parents very angry and break apart the Lego pieces they buy for you, you can't make something out of half or part of a Lego. It is always built out of discrete Lego amounts. Analogously, all energy in the universe is built up from these discrete quantums of energy. In the case of light, the smallest base unit of the amount of energy a light can carry is known as a photon. It can be thought of as a singular packet of light energy. Quantum physics deals with things at these tiny quantum levels, the tiniest scales from which everything else is built up from. The behavior of interacting molecules within our bodies, the reactions in the sun that keep us all warm, how electrons move through a computer chip. All of these are governed by the laws of quantum mechanics. There's an often misguided idea that quantum physics is some completely abstract concept. And to some extent, this idea is justified, as we can't really observe these quantum phenomena as they are simply too small. However, the understanding of quantum physics has very real applications, and already underlies much of the technology in the world around us. In reality, quantum physics is a lens through which everything in the universe can be understood, as they are all built up from those tiny quantum levels. So, a really good place to start in understanding quantum physics is with the idea of waves. If you've ever been to the beach and just sat on the sand and watched the waves approaching the shore, you've probably noticed that the waves seem to sometimes run up on each other and create bigger waves as they approach, whereas at other times they might crash and go against each other in a way that destroys each other. When the waves add to each other, it is known as constructive interference, and when they cancel each other out, it is known as destructive interference. Now imagine we have a setup where we have a wave and we pass it through two openings as such. When the wave reaches the openings, it will create two new waves from each opening that can then interact with each other. It might fill each other up in some places, as shown by the white dots, or they might cancel each other out in some places, as shown by the red dots, depending on how they interfere. The end result is that if one wanted to observe how the water waves are at a certain point, they could place a screen in front of these waves, and some parts will be more wet than others, as the water goes up at these points, and other parts won't get wet at all, as the waves will completely cancel out, which ends up creating a pattern on the screen that looks something like this. Now imagine instead we take this setup of two slits, but instead of shooting a wave through, we just have some machine that fires out, let's say, balls of paint one at a time at slits. And then quite intuitively, what one would see is just two lines straight through the slits, as there is no other way that these balls of paint could land. They would either hit the space outside the slits or between them. So now we understand what would happen if we pushed a wave through the slits, or if we were to fire particles. So do you recall those photons I mentioned earlier, those tiny packets of light energy? Imagine now we were to shoot those photons, those packets of light, one at a time through the slits. Intuitively, we might think that it would make the same pattern made by the balls of paint. I mean, they're both just firing particles through the slits. But somehow, over a long period of time, these photons of light end up making that exact same interference pattern that would be made by a wave. And so a logical conclusion to draw from this might be that photons, these little packets of light, actually just behave in waves. And that in itself might already seem a bit strange, but how else could these photons possibly get to those places that are blocked by the slits? But this is not even the weird part of this experiment, because if we tried to actually find out what was happening and observe these photons as they pass through the slits, then suddenly, instead of that interference pattern from before, we see the photons only landing in those two lines, as if they were just made out of particles of light. So, if we don't observe what's happening, photons behave like waves, and yet if we try to observe what's actually happening, they suddenly behave like particles. This is known as the double slit experiment, and it is one of the most famous experiments of all time in demonstrating the strangeness of quantum physics. So, what exactly is happening here? In quantum physics, there's a concept known as superposition, which refers to the ability of a quantum system to be in multiple states at the same time until it is measured. Essentially, because these particles of interest are so small, their behavior is not definitively determined until some form of observation occurs, and instead they actually exist in the state of being in multiple states at once. Again, this is very easy to accept at face value, that things on the quantum level can exist in multiple states at once. But hard to realize what this actually means because our normal world doesn't work like this. On a normal scale, if a coin was flipped, the result would either be heads or tails, and it is clear that only one of these options would ever be true. Even if I were to flick the coin into the abyss of the backstage, where none of you could possibly observe it right now, you guys know that that coin is definitively either on heads or tails right now, even without observing it. However, if a so-called quantum coin is flipped, the result can't be so easily determined. And thus, until more complex tools are used to actually observe the side that the quantum coin flips to, the coin actually would exist in a state of being both heads and tails simultaneously. We say that it is in a superposition of these two states. Once more complex tools are used to actually observe the side the quantum coin flipped to, the coin will then randomly be seen in one of these two states, and we say that the superposition collapses. In this case, the superposition collapses to be heads. In the double slit experiment, these photons of light are on the quantum scale. This means that as they are fired at the slits, they are in a superposition of going through both the top slit and the bottom slit simultaneously. If left unobserved, they do actually, literally, mathematically, experimentally, in every possible sense of the word, go through both of the slits at the same time. These photons through both the slits can then interfere with each other, acting like waves, and allowing that interference pattern to be generated. However, if you were to observe the photons as they pass through the slits, then the superposition collapses, as through this observation, we know exactly which slit the photon must have gone through. Even if it doesn't go through the slit that you're observing, that just means it must have gone through the other slit. And so knowing exactly which slit the photon goes through means there's no possibility of them going through both at the same time, meaning no superposition, no interference pattern, and thus they will simply act like normal linear particles. This idea is really weird to actually think about, that the behavior of real things in the universe drastically changes just depending on whether or not they are being observed. But it is the use of this property that is key to the development of quantum computers. First, I must explain how a normal computer works. Everything, including this presentation that you're seeing right now, is built up from a series of zeros and ones within a computer chip. These zeros and ones are composed of bits of data, and each bit is always set to either a 0 or a 1. This means that as another bit is added to a computer, there is one more 0 or one more 1 that can be used by the computer, increasing its functionality. However, in a quantum computer, these normal bits of data are not used, but rather qubits, which exist not only as a 0 or a 1, but in a superposition of being both 0 and 1. They could just act like normal computer bits, being set to 100% 0 or 100% 1, but they also have the chance to be in a superposition of, say, half 0 and half 1, or 80% 0 and 20% 1, and so on, for literally any possible combination of probabilities. As the computations are happening in a quantum computer, all of these various superpositions can come together and create even more and more possibilities. And thus, the processing power of quantum computers grows exponentially as more qubits are added. However, once the result is actually measured on a quantum computer, all of these various superimposed states collapse, and we are left with a result that would be identical to that of a normal computer. The difference is that the quantum computer has achieved it magnitudes of times faster. Essentially, the ability of a qubit to exist in a combination of 0 and 1 allows for the quantum computer to explore multiple trains of thought at the same time, whereas normal computers are restricted to only linear trains of thought through this restriction of being set to only a 0 or a 1. These infinite possibilities brought about by the superpositions allow for certain tasks that might have taken millions of years on a normal computer to be accomplished in a matter of minutes, which is obviously quite a significant achievement. However, the usage of quantum computers is very specific to certain problems, meaning it's not like everyone is going to be given a quantum computer. We aren't going to be given new phones with quantum chips that have revolutionary speeds. It's for specific scientific advancements involving AI, cybersecurity, drug research, chemical research, simulations, and more that quantum computers will be a true game changer. Ironically, despite how complicated quantum physics and quantum computing might seem to understand, we actually have almost all of the theoretical understanding that we would need to run and operate quantum computers. At this point, our actual limiting factor is our capability to build the hardware. Because as difficult as these concepts are to understand, you can imagine how it would be magnitudes more difficult to actually implement physically and make sure all these quantum concepts like superposition and interference happen properly without any outside interference. I won't get too much into it, but maintaining temperatures around negative 273 degrees Celsius, the coldest temperature achievable, or having a near perfect vacuum for these qubits to work in so that they don't interact with air molecules. These are all considered prerequisites for most quantum computing setups. Not to mention needing to actually design these qubits, these actual existing particles, that must act as those extremely controlled superpositions. However, if we are able to achieve a high and stable enough amount of qubits within a quantum computer, this exponential growth of processing power that I mentioned earlier would allow us to achieve computations that we could not even imagine before. This has been an extremely simplified look at quantum physics. There are many more strange phenomena such as quantum entanglement, which also allow for quantum computers to behave so differently than normal ones. However, while quantum physics might seem like some completely abstract, mathematically complex, and mainly theoretical field, its understanding has very real applications, already underlies much of technology in the world around us, and its further development in the form of quantum computers will revolutionize our future computational capabilities. Thank you.